Yes. Okay. Awesome. Cool. Ben, Victoria, Shira, Roy, Peter, Yuzi, Byron. Okay. Awesome. Cool. All right. So let's get started. Yeah, also, in case it wasn't clear, all of these bad jokes are coming from all of you from the intro survey that you guys filled out. I thought this one was kind of funny just because the person that wrote it inserted the ha 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 at the end, which is just really funny to me. Anyways, cool. So today we'll be finishing up the STL summary from last time. Doing a brief overview of classes because we're starting our new unit on object-oriented programming in modern C++. And then finally, an exciting topic, we're going to be talking about basically any questions that you guys have about the keyword const. And const is one of those words in C++ that was sort of, it was there at the very beginning of the language, but as the language has grown, has just added on more and more functionality, so it can be kind of confusing. So we'll be going over all of the weird details with const. So after this lecture, you should feel very comfortable with it. Perfect. So we're going to take the first 5 minutes to just wrap up last time's lecture. To recap, the problem that we were trying to solve was that there's a series of essays known as the Federalist essays that are about 85 of them, each of them written by one of these 3 authors. And the question that we were trying to solve was, if we are given one text from each of these authors and one mystery text, which we don't know who it's by, can we use some sort of algorithm to determine who the author is? And so I think some people told me that they've actually been working on this problem in other classes using slightly more sophisticated problem-solving techniques. But the one that we were working with here was the idea that we can come up with a list of really basic words that if we can count the number of times those words appear in a text, we can sort of treat it as a fingerprint for how that writer writes. So the idea was that for each text, we would be able to generate a feature vector of each of those common words, and then by comparing the vector with the unknown paper's vector, we can tell by how close each of them are the extent to which it's likely that that author was the one that wrote the paper. And so once again, closer the angle, the more similar the text. And the way that we are going to be doing this math-wise is using a dot product. Not important, just in case you guys are curious. So let's wrap up the coding real quick. So one more time, what we did last time is that we started off with this main file. We read in the file, converted it to a string, and now our goal is to count the occurrences that each of these words in this feature vector appears in that one long string that we created from a file. And so we got to the point where we were at this function called count occurrences, where the goal of this function was to count the number of times one word passed in here from the feature vector appears in the text passed in here. And I asked you guys to take a look at the STD algorithms library to see what algorithm do you think you'll use here, because it's actually not immediately obvious. We might think that from the function name count occurrences that we'll be using the count algorithm that we've seen before. But can someone, either from what you saw over the weekend or just off the top of your head, can someone explain to me why we can't actually use the count algorithm here to find the number of times a word appears in the string? Take 30 seconds to talk with your neighbor about it. Why can we not use count? And then if you know that, what algorithm would we want to use instead? And we don't expect you to know this off the top of your head. You can look up the CPP algorithms library and take a look at what algorithms are there. But yeah, take 30 seconds once again to explain to each other why we can't use count in this case. Okay, so I'm hearing some good some questioning ideas, some good ideas being thrown around. I'm glad that you guys are just trying it out, even though you aren't necessarily sure where this is going. Does anyone have an idea for what it may be? Feel free to just shout out any guess. Why can we not use count? All right. Yellow shirt. What's your name?
Elliot.
Elliot. Oh, Elliot. Of course I know you. Okay. Yes. What is your thought?
Maybe it's that when you're going through a string and you're going word by word, you need some way of figuring out what separates each word within a string. So there's sort of this issue with like figuring out white space delimited elements.
Yeah, so that's actually exactly on the right track. And actually, so sort of leading from that. So the more general problem here is that we're taking in a single string that represents a text. And what we want to do is we want to count the number of times a sequence of characters appears in that text. But notice if you read the documentation of count closely, it sort of goes back to this idea of that each character is the same as another. We don't have this idea of what's a word versus what's a white space. So in this case, to be clear, the reason why we can't use count is because how would we be able to use it? What we would do is we would pass in an iterator to a string, but what does the iterator of a string point to? Yeah, fire. Exactly, you got it. It points to a character, not a string. So that is the problem with using count, is that if we tried to use this function, we would only ever be able to search for a single character at a time, which isn't what we want. So this is the sort of, I think, the one tricky part with this solution. The solution to this is that there's actually another function called search, which allows us to search for, if we look here, for a sequence of elements within the passed-in iterators. So this isn't something that's really generalizable. It's just a good point to remind us, like, to go back and double check what our algorithms are doing, and also just to let you guys know that something called search exists. So, okay, awesome job. Let's see. So, okay. In that case, let's finish writing this function. So we know that indeed we now want to use STD Search. Okay. So for the sake of time, I'm not going to have us write the logic for this together, but I'm just going to give it out to you guys. Feel free to take a look at this afterwards if it doesn't make sense. But I'll be speaking my thoughts as I do it. So the general algorithm for how we are going to want to find the number of occurrences of this word in the string is essentially using a while loop. So while the string isn't over, we want to continuously find the next occurrence of that string in the text. So let's start off with the place where we want to start searching, and then the place where we want to end searching, and then let's have our count of the number of occurrences, and then we'll say while cur doesn't equal end, so while we haven't reached the end of the text, we want to use our new search algorithm. And once again, in Qt Creator, you'll notice that it tells you the arguments of the algorithm which we're using, which is just a handy tip. So in this case, I see that we want the first iterator, the last iterator, and then the first and last. And let me double check that. Yes. Okay, search is for the first occurrence of S first to S last, so the second two in the first two iterators. So what we'll want to pass in is we want to pass in the things that we're searching in between, and then we want to pass in the needle, the thing that we're searching for. Oops. Cool. Does that make sense so far? Any questions? Okay, awesome. And then we can say, let's see, if, so, right. So we're going to say, what STD Search does is it returns the iterator that points to the beginning of where it's found, or it returns it to the end pointer if it's not found. So what we're going to do is we're saying if it's not found, so if found equals end, break out of the loop. Otherwise, we have found an occurrence of the string in our text, so we increment the count, and then what we want to do is we want to set the start of where we're searching immediately past where we just found. So we're going to do cur equals found plus 1. And notice that I didn't have to do cur equals found plus the length of the string. We totally could, but notice that even by moving it 1, we've already changed it from something like the to he. So that is not a bug in our program. And with that, the last thing we have to do in our count occurrences function is return the count. Awesome. Does anyone have any questions so far? Okay, awesome. So this function of counting the number of times a string appears in another string. Hint, hint, may or may not be useful for certain assignments that you may have coming up right now in this class. Yeah, so this is a good function, and we'll be posting this code online after this. But feel free to recreate this function as well. Really, the key algorithm that we're using here is the search algorithm. Okay, and then real quickly, the last two things that we needed to finish up our program were in getting the similarity, we remember that the way that we identify how similar two texts are, or two feature vectors are, is by taking the dot product. So the last thing we need to do to print out this similarity, the cosine theta, is be able to calculate both the dot product and the magnitude. And okay, so approaching this at first glance, the first thing we need to do is calculate the dot product between the two feature vectors. This seems kind of tricky. Like it seems like we're gonna have to do some sort of for loop where we multiply two things of the same element. Should we zip something from Python, etc. Turns out our favorite algorithms library actually has something for us. Does anyone know off the top of their head what that algorithm is called? I'll say 5, 4. So this is an exciting algorithm that actually isn't in the algorithms class. It's actually in another class called numeric. And that's where you'll also find algorithms like accumulate. And then the one we're using today is inner product. Awesome. Yeah, so I'm not going to belabor this too much because at this point it's really just knowing what algorithms are out there. This is just to show that even with something that is even as sort of like theoretically complex as a dot product, the STL already has something for us. So really the key takeaway I would say when you're implementing your own types of code is if there's some sort of functionality that you think should be common enough that something should have been written for it, it is likely written either somewhere in the STL or in the Boost libraries. So I would always encourage looking up to see what tools are already out there before trying to have to recreate it on your own, unless you have to recreate it on your own for an assignment or something like that. But so if you look up inner product, what it does is it takes in the two, takes in the beginning and end of one vector and then the beginning of the second one. And then the amount that you want to start your dot product off of. So say you wanted to instead start it with an initial value of 5, you could put in 5 instead of 0. But this will actually calculate the dot product for us. And so all we want to do is return that dot product. And then for magnitude, what we're going to use for this is actually just a mathematic property. Does anyone know what the magnitude of a vector is equal to? Say that one more time.
The square root of the sum of the squares of the terms.
Exactly, yeah. So actually another way that we can write is that the magnitude of a vector is equal to the square root of its dot product with itself. And so that's just another math thing. Again, not entirely important for the sake of this class, but just to fill out our implementation. So with this, what we've done is in this function, get similarity between the two texts. We've created the two frequency vectors by counting the number of occurrences in the text. We've calculated the dot product between those two frequency vectors. And then finally, we've returned this equation, the dot product divided by the magnitudes times each other. All right, before I run the code, does anyone have any questions about this last example? Cool, are we ready to see it working then? Fingers crossed. It's always, as a general coding strategy, it's not necessarily the best. Right, square root is in CMath. And by the way, I didn't know this off the top of my head. If you're ever not sure where a function comes from, you can go to your browser, type in like square root C++, and then at the top of the documentation, it'll say what header it comes from. But yeah, it's from CMath. Yeah, as a general coding tip, I'd recommend testing early and not necessarily testing it after you've written everything. But case in point. Let's see. All right, so for the sake of time, I will debug that later. I'll also post up the original code if you guys want to try running it yourself. But that is all of the algorithms. And with that, we've wrapped up algorithms, containers. The one thing we haven't touched is templates with this. But you could imagine going back and making this generalized to a vector of anything, for example, as opposed to a vector of strings, things like that. Say if you wanted to create a feature vector on something other than words. Yeah.
Back to line 54.
54.
55.
55.
So why the fourth parameter is 0?
Yeah, so this is interesting. So what this is essentially saying is that to calculate the dot product, the only things I need to know are the beginning of the first vector, the end of the first vector, and the beginning of the second vector. We don't actually need to know the end of the second vector because this function assumes that the two vectors that you're passing in are of the same length, and or rather that you only want to calculate the dot product over the length of the first vector. So the reason, so this fourth parameter doesn't have to be vector2.end. What this fourth parameter is instead is it's an initial value. So say you wanted to calculate the dot product, but add some sort of constant in front. Like say we wanted to calculate the dot product of two vectors plus 5 or something. It just allows us to provide a starting value. I'm not entirely sure why they implemented it this way. I believe it's because there are other functions like accumulate, for which you can also provide a starting number to start accumulating from, and I believe it's just to be consistent with that format. Yeah, good questions. Yes,
Can you
Peter.
explain why this code can prevent the algorithm find the in there?
Yeah, so why does it prevent recognizing the in there as like an instance of the? So the way that we prevented that really roughly was in this count occurrences, we added a space to the beginning and before and after the word. So again, this isn't foolproof because this doesn't deal with the punctuation case. So a really good extension to this would be to go back and actually deal with punctuation the right way. And the way that you would deal with punctuation is actually using the regex library from the STL. So if you guys are familiar with regular expressions from any other classes, C++ does have something for you, and it's actually a part of the standard library. Yeah, good question. Yes, Shiran.
So if we haven't used this to find variable in this function, why do we define it there?
Say that one more time.
Because like in this function, we actually didn't use to find.
That explains why it's 0. Thank you very much.
Is that right?
Yes, that's exactly it. So rather than word, this should actually be to find. I actually don't know if that's the extent of the bug, but that is definitely one big issue. Okay, yeah, so that's not the only bug, but that is a bug. Thank you. Thank you. Good catch. All right. Any other questions? Good questions so far. Okay. In that case, I will post this code later, and I will also post an explanation of why it wasn't working in lecture, so you can see where the bug was. But for now, with that, yes, again, useful for assignment 2. With that, we've wrapped up the STL unit. So awesome job, everyone. STL is honestly one of the biggest parts of C++, that even though it's so core, a lot of people still don't really know exists or use. So cool. Okay, so before we dive into the next unit, a couple of announcements. First one is that assignment 2 part A is due this Saturday. If you've taken a look already, you already know that it's super simple. It really consists of like us testing your internet connectivity and then basically re-implementing what we just did in class. So I would just encourage you to get that done by Saturday. Yeah, if it's taking more than 2 hours, please come talk to us. And then by request, online, we will be releasing part B after this lecture, either today or tomorrow. The deadline will still be where it originally was on Thursday, November 14th, but this way, if anyone wants to start early, they can. Yeah. Awesome.
Can I add something?
Yes.
Oh, yeah. So assignment 3 will be released, I think, November 10 or something. Yeah, because we want to release it just a little earlier, just so that you don't think we're trying to force you to do something over Thanksgiving. Okay? You don't have to do anything over Thanksgiving. We just want to give you some extra time so that you have some breathing room between that day and Thanksgiving and week 10. All right?
Yeah.
I'm assuming most students aren't going to do assignment 3, which is a little sad, but but if you are doing assignment 3, just a heads up that we'll be releasing it a little early.
Yes, that's right. Yeah. So yeah, reminder that you only have to do 2 out of the 3 assignments in this class. Yeah, Mason.
Oh, no, sorry.
Okay,
No, I was just.
Do you have a general idea of when assignment 1 is coming back?
Yeah, assignment 1 should be coming back. It'll be coming back a bit before assignment 2 is due. The main thing is because, yeah, the graders, we passed on to the graders and we want to give them enough time to grade and provide comments.
Yeah.
Yeah.
Because the graders, they're also grading the 106B midterm this week, and then they also have to grade Boggle like the next week. So we want to just give them a little more time. They all have their own sections to take care of. So just give them like a week or 2, and they'll have everything done.
Yeah, the other thing is that with the feedback for the assignments in this class, since they're primarily about functionality, not as much about style, so the grader comments will also be less detailed than you might have been used to from like A, B, or X. So if you guys do receive feedback and or want more detailed feedback, like please come to us in office hours and we can also like sit down and walk through your code and like take a look more closely, because the assignment graders will likely be providing like some general yeah, either bugs or feedback advice. Cool. Awesome. Okay, so how many of you in this room are familiar with object-oriented programming? Can I see a raise of hands? Okay, awesome. Okay, good. So I see there are some for whom this will still be useful, and for the rest, I will also still, I guess, go through it a little more quickly. So C++, as we mentioned before, is not an object-oriented programming language solely. That is one of the ways that we can use C++, but you can also use C++ as a functional language, et cetera, et cetera. That said, OOP is one of the most common ways that people use it. So it'll be the focus of pretty much the remainder of our lectures, minus a couple of the last ones. So as a reminder, sort of where we're going to, I guess, specialize OOP to this class. When it comes to polymorphism, we'll be talking about operator overloading and virtual functions over the next couple lectures. Template classes get to this idea of abstraction in OOP, and then inheritance is inheritance, which we will also be talking about. And then classes, objects, and encapsulation. All 3 of these terms should actually be familiar to you from CS 106B. Has anyone, I actually am not sure, has X covered this, and or is anyone not familiar with these 3 concepts? Okay, all right, yeah, and if you aren't and you don't feel comfortable, please talk to me after class. So just a brief review of classes to make sure we're all on the same page. First is, if you aren't familiar with those, or if you want to review, Cynthia just covered it, I believe, last week or so. So yeah, please look over those slides. What you guys covered in 106B, if you are in 106B, you should have seen the use of .h versus .cpp files. You should be familiar with basic constructors and destructors, basic const, basic operator overloading. So that's what I'm assuming that we're coming into the class with. And a couple of notes on these. So the first, can anyone tell me what is the difference between a .h and a .cpp file? Raise your hand. Yeah.
.h lets you like define the class and the functions within the class, where the .cpp file is the actual implementation of those things.
Exactly, yeah, exactly. So as Mason said, the .h file is where you can define the class and the functions within the class, whereas the .cpp is where you implement those. An even more general way to think about it is that the .h is where you are specifying the interface for your class. So that's sort of the public-facing like API that you want other classes to be able to use from your class, whereas the .cpp is where you're hiding all of the dirty details. So you might have heard all of that before. But yeah, again, this is from the 106B lecture that Cynthia gave. So small details about header files. We won't necessarily be concerned with these, but if you're not familiar, I definitely encourage going back and taking a look again. One thing you might notice is that at the top I've written header files, .h, .ah, versus source files, .cpp, .cc, etc. And you might be wondering, what is the difference between all of these extensions? And this is a perfectly valid question. In fact, it turns out there are even more extensions for .h and .cc. There's .hpp, .csx, .cxx, .c++, .C. Quite confusing. So this is just fun trivia facts / slightly important in some small edge cases. That's my reaction when I see that. It turns out that which extension you use depends on the compiler. So if you take a look At this link at the bottom, there's actually a list of which compilers accept which extensions. For example, GCC accepts, I believe, 4 out of the 5 CPP extensions, etc. And for your knowledge, the .C was actually the original C++ extension, but the confusion came when file systems started making file names non-case sensitive. In other words, .C and .c would start meaning the same thing. So that's where they started coming up with .cc, .cpp, and now it's sort of the general standard is that any Unix systems, Unix Linux systems use .cc, any other systems, so Windows, for example, will use .cpp. And really, the one case where this matters might be where you are mixing C code and C++ code. So if that ever happens, take a look at extensions again. But yeah, this is mainly just interesting things because I know people have always been confused about that. So constructors, again, this is just from the 106B lectures. This should look familiar. We'll actually be getting into more complex constructors in this class. So copy constructors, move constructors, things like that, which Avery will be covering.
Next week.
Next week, in fact, yes. Destructors, honestly, we won't be going too much more in depth in this. Yeah, basic idea is when an object from a class, or when an instance of a class goes out of scope, it calls the destructor. That's usually where you're freeing memory and things like that.
Yeah, towards the end of the class, we will talk about this important concept called RAII.
Yes,
Yeah.
that is true.
Is there an easier way to pronounce that? RAII.
RAII.
Okay, well, there's a, like, the single most important C++ idiom is called RAII, and it has to do with the destructor. So we will talk about that. Yeah, it's like one of the things that makes C++ unique from all the other languages.
Awesome. Okay. Yeah, so actually, let me get through these. So you may have also seen from the 106B lecture, Cynthia should have mentioned these 2 uses of const. One that you should have seen from this class and from 106B or X is using it as a parameter. So a const parameter that we pass by reference is very common. The other one that you now have seen is that using const as a function, so saying that a function is const. Can someone summarize for me what a const function does? It sort of says it on the side, but yes.
They can't modify the other particular function like variables.
Exactly. So a const function can't modify any of the class variables or any of the variables that are passed into it. Exactly. Awesome. And then today what we'll be doing is actually going over everything else that's const. So this is sort of just scraping the iceberg, but this is actually one of my favorite lectures. I think I'll be using the lecture slides of one of the previous lectures, and I think it's super funny. But before we get to that, one last thing is operator overloading, which Avery will be covering next lecture.
Did Cynthia really cover operator overloading?
Only very briefly.
Very briefly?
Only
Okay,
very
okay,
briefly.
cool. So,
Nothing like friend.
Okay, I'll also have enough to talk about next lecture.
Absolutely. All right, so before I jump into const, does anyone have any questions about OOP, classes, general review? Okay, who's excited for const? Okay, oh, hey, I see that hand. Awesome, yeah, so const was actually one of the keywords that confused me when I was first learning about C++. Sort of like, I had seen its common use cases, but I had also seen it in some weird use cases and wasn't sure what exactly it meant. Okay, so we have 22 minutes, and I believe we may or may not finish the entire slide deck, but we can cover the last 2 miscellaneous topics next lecture. Okay, so yeah, thank you to Mike for using his slides. Okay, so I'm just gonna give you guys 30 seconds to read this because I think it is very common. It's the general question of why do we use const at all? And apologies for the small font. There we go. And that is our words of advice from Erbsetter, our generally cool dude. So yeah, so the whole idea of why use const, yeah, and sorry if that wasn't enough time for you to read it. These slides will also be online. Yeah, so before we do that, actually a more general question, why don't we use global variables? you might have heard this before. Well, global variables can be modified or read by any part of the program, making it very difficult to reason about their use. They can also be get or set by any part of the program, and generally are just seen as unsafe. And the exact same thing with const. So really, it's more than a style thing we'll see. Using const is actually very good for both ensuring the safety of our programs. Yeah, generally it's safety, style, and sort of ensuring that the interface that we're promising is actually the interface that we're providing. Awesome. Okay, so another motivation for why const. Can anyone spot the bug in this code? Take 30 seconds to talk with your neighbor and see if you can find what will cause this code to do not what we expect it to do. It's a little hard to see. All right, actually, sort of a trick question. It's basically impossible to see. You'll notice over here, actually, this is a bug that happened to me that actually took me 3 hours when I was going through CS106B to debug. So this is very near and dear to my heart. But you can obviously see this code is sort of a contrived example, but as you build more and more complex databases, the promises that you make become really, really key to making sure that your code is doing what you expect. So if we had used constant x and constant y instead, since we are only c-outing things in this function, we would have received this error, and that would have let us know. That said, is that all that const is good for? Is it only useful for providing us compiler errors where we wouldn't have seen before? No. So let's take an example of planet Earth. Okay, let's say we're like some geologists and we want to do something benign, such as counting the number of people on Earth. So we call this function count people on Earth, and we expect it to return some sort of population amount to us. However, some malicious Santa Claus in our function has actually implemented this count people function to have this function and add little hat Earth. And so while we are running, while all we want to do is count the number of people, it turns out we've actually also added a little hat to Earth and turned it into Mars and shot it to death with a Death Star. All that we were trying to do was to count the population of Earth. And so how did this happen? So exactly as we said here, when we called the count people function, it called 3 functions that actually modified the Earth object that we passed in, which we did not intend at all. Yeah, some political commentary here. So what would have happened if we had made this a const method instead? So one more time, if we had made this, instead of a planet P, a const planet reference P, what would have happened, once again, is that the compiler would have saved up and let us know that we were passing in the wrong argument. And the reason why this is important is because when we are designing classes for other people to use, we first want to make them const whenever possible, and second, want to let them know that we have made them const so that they can use it as they intend. Yes, they allow us to reason about whether a variable that we pass into this function will be changed or not. So it's useful for our clients, not only for us. And with that, the Earth will also not be destroyed. So one more time to reaffirm, when we pass in const, when we pass in parameters to constant methods, they are guaranteed to not change the value that we pass in. And so we know for a fact that the value of x at the top is the same as the value of x at the bottom. Okay, before I continue on, are there any questions so far? Yeah, Elliot.
Is the assumption that the functions within the function here, or like 3 functions within the count people function, are taking x by reference and not const themselves?
Yeah, that's a great question. So am I interpreting your question correctly to be that if we're passing x not by reference, then they wouldn't be modified anyways?
Yeah.
Yes, exactly. So a better example here would have been to use, instead of an int, say a planet object or something like that, where we would want to pass by reference regardless to save on space. And so the const keyword really matters. Or for example, for any non-primitive types, where we want to pass by reference for space, but still need some sort of guarantee that it won't be modified. Yeah, good question. Yeah, Peter.
Will it return a runtime error, or is compiling time?
Yeah, great question. So when it comes to const, will it return a runtime or a compiler time error? The great thing about const is that it returns a compiler time error. Yeah, so the compiler can do all this checking for us as to whether we've accidentally modified something we weren't meant to modify. Yeah, good question. Yeah, any other questions? Yes, Shiran.
If we define f as const x, do we need to also make these two methods as const, like they receive the const parameters for x?
So as in, if we had changed the x parameter to be const int reference x, would we also need to modify this x parameter to be const int?
Yeah.
Yeah, that's a great question. So the answer is yes. So one of the things that const does, which is the reason why it works, is that it not only ensures that this first level function is all const correct, but also that any functions that you call from there also satisfy the const property. Yeah. And so what'll happen if you don't do that is you'll see a compiler error saying trying to pass in const object to non-const function, something like that. Yeah, Byron.
So going back to the nice quote you had earlier.
Yes.
Using like a library that does not follow proper const. Is there?
Say that one more time. Is there?
If you're using like some external, like someone else's library, someone else's code, and have const correctness. Is there anything you can do about that?
Yeah, good question. Yeah, that's a great question. So what happens if we try and use a library that isn't following these nice const properties? Avery, you might have feel free to jump in on this, but my first response would be, then in that case, it is really just up to us as the client to make sure that we are enforcing on our end that the parameters are modified. In the example such as the count people case, let's say that we didn't know how count people was implemented. That's where it gets into murky territory. Yeah, and I can't think off the top of my head of okay. Actually, one way to prevent Earth from being blown up in that case, for example, if you know that you won't need to modify it after initializing it at all, then what you can do is you can declare Earth as a const variable itself. And that'll prevent it, even if it's passed in to a function that tries to change it, then it will still throw a compiler error. But if you do need to modify Earth and then also have to pass it in, I believe you can pass it in as a const version of itself, actually. I'm pretty sure.
Okay. I'll just add on to Anna's answer.
Yeah.
So is your question that the library itself is not const correct, so it doesn't do anything const, but you declared some variable as const and you can't pass it in? Right? Is that the question?
Well, if you wrote like a method that takes in some variable as const, and then you call it non-const.
Oh.
Yeah.
Oh, okay. Oh, yeah, I see. Thank
yeah.
you. Yeah, no,
okay.
you got it.
Yeah, so that's definitely not ideal, but there is a way around that. There's this thing called a const cast.
Yeah.
Which basically lets you cast away a const. Now that is not good in that it's basically someone else's code is bad, so we're gonna propagate the bad thing onwards. So generally not a good idea, but if you really had to call their function, then you would make it. You would use a const cast to cast the const away.
That's a good point. Yeah, so either if you have a const object, either you would not be able to call that function and it would throw a compiler error, or you would have to const cast yourself. Although in that case, I would question why you would want that variable to be const in the first place if you know that you'll be changing it at some point. Yeah. But yeah, good question.
This shows how important it is if you are implementing some library. You have to make sure your code is const correct. Otherwise, whoever uses your library will have a really hard time. And also, just side note, CS 110 on some of the assignments they use const cast because their starter code is not well written.
Yeah, and actually something that we'll see, I don't know if we'll have time to get to it this lecture, and or I forget if I actually included it in these slides. Actually using const cast is how we implement overloaded functions in classes where there are both const and non-const functions. It turns out the best way to implement those is actually using const cast. So there are purposes, but yeah, in general, when we're writing our own code, we want to avoid discarding constants. Yeah, good questions. Any other questions so far? Okay. Awesome. Okay, so the second thing that we saw was that, yes, we can not only make parameters const, but we can also make functions themselves const so-called const member functions. So to get a feel for that, how does const interact with classes? Let's say that we have some cloud defining an object class where it has a bunch of private member variables that we don't need to worry about. Previously, the way that we've sort of thought about classes is that, okay, we have an object class and we have functions that work on that class. And now what we realize is that, in fact, those functions can be divided into two types. One is a const member function, or it can be a non-const member function. And in fact, a non-const member function is able to work with both const and non-const variables, whereas a const member function can only provide the const interface. So as an example of that, going back to our example, we see that we've defined this count population function as a const function and the def star as a non-const function. So let's say that we declare some sort of, or let's say that we have a function that takes in a constant parameter. If we then try to call the constant function on a const parameter, we are able to do so. However, if we try to call a non-const function on a const parameter, we are unable to do so. So, sort of intuitive. But yeah, does anyone have any questions about that? Does everyone understand why this will not compile, this last line? Sort of going back to what we said before about how const ensures that everything down the line of it as well is also const. Okay. All right, so one of the trickiest things with const, I think, is when it comes to const pointers. We'll go through this one, we'll take our steps slowly through this one. So this first example, an int pointer to a const p is a constant pointer to a non-constant integer. In other words, what you can do is you can dereference the pointer and change that value and set it to something else, but you can't change the pointer itself. So another way to think about this is that you have the pointer finger, you're allowed to change whatever it's pointing to, but you can't move this finger around. Does that make sense? And so the way to read that is, again, going right to left. You have a const pointer that points to a non-constant int. On the other hand, you can also have a const int pointer p, which is a non-constant pointer that points to a constant int. And again, reading right from left, and same with this one, same syntax, different syntax for the same concept. And then finally, we can also have a constant pointer to a constant int. Does that make sense? Does anyone have questions? How comfortable do we feel with this? Okay, no, I'm seeing no's. Okay. One more time, the difference between the three of these, again, this only occurs when you are working with pointers. So this would happen when, say, you're working in C and or working with pointers in C++, such as when you declare something on the heap. So this is, again, how const interacts with pointers is that there are two things that you're working with. You can either have a const or non-const pointer, meaning that the arrow itself, the finger itself, is or is not allowed to move. So in the cases where it says const pointer and const pointer, you know that the pointer is not allowed to move. And you can also control the constness of the thing that the pointer is pointing to. So in this case, the pointer is of type const int, meaning that you cannot change the int that it's pointing to. And in this case, the pointer is of type const int, meaning that you cannot change the thing that the pointer is pointing to. So one more time, you can read it from right to left. The very first one has a const pointer and a non-const thing that it's pointing to. The second one has a variable pointer. You can move the pointer itself, but whatever you're pointing to, you cannot change. And then the last one, you can't change anything. Okay, and we'll look at a quick example of that at the end as well, in case that that doesn't make sense. But take a look at it again. Remember that you can just divide it up into those two segments. And again, everything applies the same when you're working with objects instead of primitives. For example, if you had declared a widget on the heap or something like that. Yes, so using pointers with const is just a tad bit tricky. Okay, when it comes to iterators, how iterators interact with const, iterators actually, more than act-like pointers, are actually a superset of pointers, but we won't get into that for now. the key tricky thing with const here is that a const vector iterator acts like the instar const iterator. In other words, when we say const and then an iterator type, we are saying that the finger itself cannot change, which is the same as the instar const iter. That one is again saying that the iter itself is the thing that cannot change. The reason why that's tricky is because if we want to make it so that the thing that we are pointing to by the iterator does not change, we have to define a new type called a const iterator. So if you've been looking at the C++ specifications online, you may have seen that every class comes with both an iterator and a const iterator, and that's the reason why. So again, say we had a vector that contained 1 and 2, 3, 1, 2. A const vector iterator means that the iterator itself cannot be changed. Your finger cannot be changed, meaning that you can't increment the iterator, but you can modify what that iterator is pointing to. So in this case, it would replace the 1 with the 15. Does that make sense so far? Any questions? Okay. And again, to reiterate the difference between the two, the first one can change what the iterator points to, but not the iterator. The second one cannot change the iterator. Cannot change what the iterator points to, but can change the iterator. All right, yeah, this is also, if you aren't getting this, feel free to take a look at the slides. And then, yeah, const iterators, I think, pop up a little more often in C++ than const pointers. So I just take a look at the slide and make sure that you understand what's going on. But remember, I think the key thing to take away is that you are always working with two types of const when it comes to pointers and iterators. One is whether the pointer iterator itself can be moved or not, and one is whether the thing that it's pointing to can be changed or not. Awesome. So as a recap, yes, Byron.
Can you use const with an auto to technically like an auto iter?
Great question. Yeah, can we use const with auto? Absolutely. So const and then the reference, the ampersand, are two things that auto does not take care of. So yeah, so you can absolutely use const with auto. Yeah, good question. Yeah, any other questions? Okay, so as a brief recap, so you guys have just seen const in more places than I believe most people have ever seen them. So we've seen them in terms of all types of arguments, local variables, return values, and also in terms of functions. So functions can be const. And as a challenge for you guys, I guess this would be the extra challenge if you guys want it that we have posted on Piazza, is to understand what this function is doing. And it looks intimidating, but I promise if you break it down one const at a time, you can translate exactly what it means. And so at the beginning of lecture next time, I will post a slide that explains what each of these consts is doing. But yeah, this is a good challenge. If you can understand what this is, I have to say that you will have completed the const certificate of excellence. Okay, yeah, so again, take a look at this slide after class. And then sort of the second part of the recap, in general, for philosophical takeaways, when you are writing classes of your own, you want to mark everything that does not get modified as const. It's more than just a stylistic thing for whoever's reading it. It's actually important to the effective running of your code and usability of your class by other people. Passed by const reference, so const object and like value is better than passing by value, except for primitives such as bool, int, double, things like that. The third bullet point we will be talking about later, that goes back to the const cast thing to define both const and non-const functions in classes. And then, most importantly, we love Earth and don't want to go to Mars yet. Awesome. So take a moment to read this. It just is a summary slide explaining the differences between objects and functions const. But then after that, that's all I have for you today. And next lecture, we will be talking about operator overloading in classes. But yes, and these slides will all be posted so that you guys have a reference for how to use const as you go out into the future. Cool. And then, yeah, Byron.
So this is, if you have like a const object,
Yes.
let's say you had like some data you wanted to get from the user.
Say that one more
So
time.
you had some data and you wanted to like display that the user cannot modify.
Yes.
Would be like a good way of, since
Right.
it like freezes all the number variables.
Wait, I didn't hear that last part.
Like if you have like a const object,
Yes.
you make all the member variable, public member variables, const as well.
Yeah, you totally can. Yeah.
Yeah,
exactly.
yeah. You might wonder what do you do about the constructor when you want to initialize the member variables. We'll discuss more about this next time. You'll have to use this thing called the initialization list. Yeah, because if you declare a const object, then you can't, in your constructor, you can't even initialize the private member variables.
Yeah,
So the way
that's
around that is to use a initialization list, which we'll cover when we cover constructors. All right.
Awesome. Good job, everyone. Good luck or congratulations on midterms if you finished, and we'll be taking questions outside. But thank you for coming today. Yeah.
Also, was anyone planning on coming to my office hours tonight? No? Great. Okay, great. Because I might have to move them.
Yeah, I may or
So-
may not also be canceling one of my office hours this week, so keep your eyes posted on Piazza.
All right, thanks for coming. All right. I'll make sure I save everything.
Okay, stop recording.
Stop recording, yes.